Dear all, this is a short recording just to explain the unclear parts in lecture 4 of the potential energy. When we discussed the potential energy and the techniques to calculate potential energy. So let's take a look here. I have the MOE window, and in it I have drawn I drew this hydrogen molecule. It's just two H's. And you see when I select these two H's, we have certain distance here. So the distance is 0.652. So when I stretch this H, let's stretch this, so we make it like 0.8 angstroms. And we calculate the energy, calculate potential energy. You see that we have a certain energy associated with it, like this, the energy of this molecule is 4.5. Okay, let's minimize this molecule. Minimize. And then let's compute the potential energy. So the potential energy is now 0. The potential energy is now 0, which means that there is an optimum bond length, which is 0.652, and if I stretch this length beyond that optimum distance, the energy increases. So when I did a stretching here, the energy increased. So what would happen when I do a compression? When I go to 0.5, let's see. Let's compute the energy again. Here we see it. It also increased. So if I deviate from a certain optimum bond length, the energy increases, and this happens as well for water. Let's try the water molecule. Let's try a water molecule. So I will go to builder, and I will build a water molecule. So this is an oxygen and two hydrogens, and we have here an optimum angle. Let's see what angle is it. The angle is 107. Okay, so let's compute the potential energy. Let's minimize first. It shouldn't change, and then compute potential energy. Okay, so everything is 0. So we have optimum bond lengths and optimum angle. So if I change this angle from 103.99, I make it 108, for example. Let's see what would happen. So this is a little bit. Let's make it more. Let's make it stunningly clear. I will make it 130 or 140. See, the water molecule now is more. The angle is more obtuse, and we calculate the potential energy. Sorry. Let's calculate the potential energy. See, we have now an associated penalty for the energy. It's now 14. So it used to be 0. Okay, so let's go back to the optimum. We'll do minimize. We're back to 104. Let's make this 90 degrees. And then we calculate the energy again. There's also an associated penalty. So it used to be 0, and now it's 3. So whenever we deviate from an optimum bond length or angle, there is an associated energy penalty. That's the take-home message. Whenever we deviate from the best or the equilibrium bond length or angle or dihedral angle, there is an associated penalty. So that's the first thing. Let's take a look at this molecule. So I will draw a little bit bigger molecule, something like this. And then I'll put some I think this is enough to illustrate the idea. I will do energy minimize, and then I will compute the energy. So let's see what's going on. So the energy is not 0 here. The energy is not 0. There might be some associated problems, associated penalties with the energy. So I know it's negative. This is just because of some definitions of potential energy. But in the end, it doesn't have to be 0. So if we have a big molecule and we do energy minimize, we don't have to have a 0 here, because not necessarily all bond lengths and angles are in their equilibrium position, and even if we minimize, sometimes we don't reach equilibrium for all dihedrals. Like there is still some associated penalty or associated favored conformers. Okay, so that's the first part. So the first part, it's the important part that I want you to know, is that there is an associated penalty. Where did we put it? Here. We assign energy penalty to each of the items, to each of the bond lengths, angles, and dihedrals. And the total energy that we get in the end is the sum of all penalties. And the penalty is defined as any deviation from the optimum value. It's any deviation from the optimum value is associated with an energy penalty. Okay, so now I want to take one step further and ask myself, how did we compute? Like when I press compute here, what did the computer do? The computer would use one of two methods, the ones that I described in the very beginning. Either molecular mechanics or quantum mechanics, or actually there's a third method which is a hybrid of these. It's called semi-empirical methods. So the quantum mechanics is the natural system, the natural mechanics that is used for the system. And as I explained in the lecture, this is it's a set of equations that solve the molecular system, and it is the natural way to solve them. Like the natural way to study, for example, a car that is moving on a highway is using Newtonian mechanics. You know, you calculate the friction, you calculate the speed, you calculate the acceleration, and you have some laws that you can put all these in, and you will get the parameters you want. But the for quantum mechanics it's different. For molecules and atoms and electrons it's different. You cannot use the same mechanics that you use for big objects. You have to use something called quantum mechanics. And it does not involve any parameters or any approximations, or sorry, it has some approximations, but it does not involve any parameters from experiments. Like, to use quantum mechanics, you don't need to provide the computer with any parameters. What do I mean by parameters? I mean by parameters equilibrium bond lengths and equilibrium bond angles for a certain atom type. For example, let's take a look here. We mentioned, let's delete this molecule first, and we put the easy molecule, which is hydrogen molecule. Okay, so for the computer to calculate the potential energy, we said that any deviation from the optimum value is associated with an energy penalty. So this means that the computer needs to know what the optimum value is. So you need to provide it in advance with the optimum value. This method that the computer is using now, which is very fast, is called molecular mechanics. It is this method, the one on top. But there is another advanced method called quantum mechanics. For quantum mechanics to work, you do not need to provide it with the equilibrium bond length. Like, you don't have to tell quantum mechanics what the equilibrium bond length is. It will calculate the energy, even if it doesn't know anything about the system, like its equilibrium bond lengths, bond angles, and so on. But the problem with quantum mechanics is that it is it is a little bit involved. Like, it needs lots of time. Let's see. The important piece that I want you to know is this table. Where is the table? Here. The difference between quantum mechanics and molecular mechanics. In quantum mechanics, we do not need parameters. In molecular mechanics, we have to have parameters because the calculation depends on it. Because we are studying deviations from equilibrium, bond lengths, and bond angles, and dihedrals. So we have to have these equilibrium, bond lengths, and angles, and dihedrals. And then any deviation from these is associated with an energy penalty. And the computational cost in quantum mechanics is high. In molecular mechanics, it's low. Speed in quantum mechanics is slow. In molecular mechanics, is fast. And very important, quantum mechanics is applied to only small systems, while molecular mechanics is applied to bigger systems, up to thousands of atoms. So if you want to study a protein, quantum mechanics, yes, it's very accurate, but it's not applicable. Nobody would ever study a full protein with quantum mechanics. So we will study the full protein with molecular mechanics. Sometimes they do hybrids, like they study part of the protein with quantum mechanics and the remainder of it with molecular mechanics. But I'm talking about the general idea is that molecular mechanics is applicable to the larger and bigger systems like proteins. So if I ask you about what is the proper way to to optimize a protein or to minimize a protein or something like this. Of course, it's molecular mechanics, it's not quantum mechanics. And quantum mechanics has high accuracy. Molecular mechanics has high accuracy as well if the parameters that are used are good. And I want you to associate in your mind molecular mechanics with parameters. Molecular mechanics with parameters. Quantum mechanics is parameters free. There are no parameters in quantum mechanics. Only in molecular mechanics do we do have parameters. So of course I will not go through everything now. I'm just highlighting some issues. Yeah, and I told you that semi-empirical methods is just a hybrid between the two. What else do I want you to know? Let's see. Yes, scope of the method, energy penalty, parameters. Yes, parameters. Where do we get the parameters for molecular mechanics? We said that for molecular mechanics, we have to have parameters so that we can do the calculations. The parameter is something like the equilibrium bond length. So where do we know the equilibrium bond length so that we can use it in to derive a certain force field that can be used in molecular mechanics? We can know this from experiments. Like there are some experiments that can give us those values, or we can use quantum mechanics itself, because we said that quantum mechanics is an ab initio method, meaning that it starts from the first principles. We do not need parameters, so we can use it to derive these parameters and then use those parameters later in molecular mechanics. So that's enough for to highlight the main points here. If you have any questions, please contact me. Thank you.